So I did this lesson earlier with my calculus class, and I realized I didn't want to record it then. I wanted to wait, and I'm glad I did because there's a lot going on. So I'm going to break this up into several videos. We're talking about the derivative. Okay, this is the first time we've really used this word formally. We're going to explain exactly what it is. We're going to take a look at the graph, and we're going to learn what the difference quotient is, the definition of the derivative. So this first part of the video is going to be focusing on where that definition comes from, why it's important. What I thought I'd do first is take a look at a graph of what would be a car traveling, and we're going to go from there. Okay, so here we have the graph, and I know there's a lot going on, so I'm going to try to explain every single one of these components. You can see my mouse moving here. But basically, this black graph right here, let me take kind of all this stuff off first, and we'll go back and look at it. This graph right here represents a car, and the x-axis down here represents how many seconds have elapsed. Okay, so of course it starts at 0. The y-axis right here represents how many meters it's gone. So after so many seconds, it goes so many meters. And right now we're going to focus on the point 5. After 5 seconds, okay, this car has gone 6.25 meters. Fair enough, right? Well, the derivative concept really comes into play in calculus when we think about if we're given this graph of the car and its position graph of the car, what if we want to know how fast the car is going at 5 seconds? Okay, we know it's traveled 6.25 meters, but what is its actual speed? What is its actual velocity? That's where the derivative really comes into play, and to me, that's the best way of thinking conceptually about the derivative. So what we're going to do is we're going to plot another point on the graph. So this point is 9, 20.25. That means that after 9 seconds, this car has gone 20.25 seconds. All right, fair enough, right? Well, in this class before, we learned the concept of average rate of change, which is the slope of that purple line that we just drew. And basically, the average rate of change, we'll go ahead and show our rise over run, is just the distance traveled divided by, how long the time, basically. So in this particular case, it looks like they traveled, 20.25 minus 6.25, so 14 meters, and they did it in a matter of 4 seconds. If you divide 14 over 4, you get 3.5 meters per second. That would be their average velocity from 5 to 9. But again, the question remains, how fast is it going after 5 seconds? And we've talked about the concept of instantaneous rate of change, and that's its speed, right? And so what we normally do then to figure that out is we drag this green point closer and closer to the black point, and its average rate of change becomes its instantaneous rate of change as the green point becomes the black point. It's the slope of that orange line, and as you can see, the car is going 2.5 meters per second at 5 seconds. So what does this have to do with derivative? What's the difference between derivative and instantaneous rate of change? Well, the formula that I taught you guys for the instantaneous rate of change is one form of the derivative, and in fact, they are the same, okay? If you say instantaneous rate of change, it's the same thing as derivative, okay? The instantaneous rate of change at 5 for this car is the same as derivative, which is the same as its speed. But just for now, know that the best way to think about the derivative is, how fast a function is going. In other words, how fast is that car going, if you will. So we're going to go ahead and take a look at this graph, but we're going to break down what we just did with some variables, and we're going to use these variables to come up with a formula for the derivative, which again is called the difference quotient. So this initial x value, which was 5 on our car graph, we're just going to call x because, we could have in the graph, we could have figured out how fast it was going at 6 or 7 or 8 seconds. It doesn't matter, so we're just going to call it x because it needs to change. That second point we put on the graph to find the average rate of change, that second x value, we're going to call x plus h. And the reason we do that is because the horizontal gap between x and the second point, we call h. And so the concept is, as we drag this point down closer and closer to this point, okay, h is going to approach 0, and we will see that more and more. I'm going to bring this, up again, but basically, your gap here for right here is 4, right? It's the difference between 5 and 9. And as we drag 9 closer, okay, h becomes smaller and smaller. In other words, the horizontal distance between those 2 points. So that makes sense then that this second x value would just be x plus h, okay? And again, we want h to be as small as possible so that it can become the tangent line. When h becomes 0, then we have the tangent line, which is drawn. So what are the other two components? Well, obviously the first y value we're going to call f of x. In our car example, the first y value is 6.25. It went 6.25 meters. The second f value is just f of x plus h, because your second x value is x plus h, okay? So if you wanted to talk about what that y value is, it would just be f of whatever that is. And again, the corollary for the car example, our second x value was 9. Our f of x plus h would have been 20.25. So, you know, how do we put all this together to talk about the derivative? And just keep in mind that the instantaneous rate of change, okay, is the derivative. But for now, this is going to be our equation, and I will break it down, you know, to a t, so don't get overwhelmed right now. But for right now, this is the equation for the derivative. And again, we're going to break down each component, so don't get, you know, too worked up. We're going to talk about why that is. And also keep in mind that h is a really, really, really small number. In other words, we want that horizontal gap to be as small as possible. We want to bring this point closer and closer to this point until it virtually becomes that point. What I want to do is compare the instantaneous rate of change graph with the derivative graph. Basically, the concept we learned about the limit of the slope of the secant lines is the same as what we're doing now. Before, we called this first point x1, okay, and we called the second point, the x value for it, x2. So naturally then, the second y value would be f of x2, the first y value would be f of x1. Notice how all of these things are similar though. So it's just different notation. Before we had x1 and x2, but now we're focused more about this horizontal gap we call h. So your second x value is called x plus h. And again, you know, since your second x value is x plus h, your second f value is f of x plus h. And so notice, if you do f of x plus h minus f of x, you get your change in your f value or your change in y. Okay? So notice, this is the first formula we learned. The limit as x2 approaches x1 of f of x2 minus f of x1 over x2 minus x1. We called that instantaneous rate of change. In fact, that's the same thing as the derivative formula. The limit as h approaches 0 of f of x plus h minus f of x over h. See, f of x2 is just f of x plus h. F of x1 is just what we call f of x. And then h is just the difference between your x values. It's this gap right here, x2 minus x1. So they're the same equation, they're just written in different ways. They mean the same thing. This is kind of reiterating what I just talked about, but h is your x2 minus x1. You could rewrite x2 as x1 plus h, okay, because it's just the first x value plus your gap. And you could virtually just call it x plus h, right, because it's your first x value. So then your second x value must be f of x plus h. So that's it. Those are the components. Now, we learned the concept of the limit. To be honest, a large reason why we did that is because a derivative is a limit. And what's happening is your x2 value is approaching x1, meaning that gap between your x values is approaching 0. So again, this horizontal gap is closing in on itself. Going back to the car example, these two x values are getting closer and closer to each other. In fact, see if I can pull this up so we can see it. In other words, your seconds, okay, the change in seconds is approaching 0, as you can see down here. And when it becomes 0, you have your derivative graph, or your slope of the tangent line. And remember, the tangent line is your instantaneous rate of change. But we can't divide by 0, right? So because of this difference quotient, we can't just have a 0 for h. H has to approach 0. And we talked about that with instantaneous rate of change. Is basically you want to find 2 points as close as humanly possible. In the car example, the closer the 2 points are, the closer your average rate of change equals instantaneous rate of change. So that, therefore, it's a limit, and it's the limit as h approaches 0. When you put it all together, you have the limit as h approaches 0 of f of x plus h minus f of x over h. In other words, your change in y values divided by your change in x values as your x values get closer to each other. So what are we saying? We're saying the instantaneous rate of change is the derivative. So from now on, we will say instantaneous rate of change from time to time, but derivative means the same thing. I want to point out that for the difference quotient formula, when we're talking about the derivative, it is a formula, it's an equation. So normally when we say the derivative of a function, in other words, how fast is it changing at a certain x value, we use this notation, and we read it as f prime of x. Okay, it looks kind of like an apostrophe. So f prime of x means the derivative at a certain x value. In our car example, the x value was 5. Okay, it's the value of, let's see if we can get rid of some of this. It's the value of that black point right there. So let's read this together. If we want to read this, which again is called the difference quotient, which is the derivative of f of x is equal to the limit as h approaches 0, as our two x values get closer to each other, or our time values in terms of the car, of the difference quotient. So this is called the difference quotient. It's the change in y over change in x. It's the same thing as when you learn slope in Algebra 1, okay? It's just now we're talking about curves and other things, but it's still the change in y over the change in x. So that's actually it. I'm not going to do the first example in this lesson. We'll do it in the next lesson. We're going to do some proofs. But that is the difference quotient explained. I will leave a link to this app so you can play around with it and see how this illustration of a car and its position graph, how that correlates to the derivative and where the difference quotient comes from. If you have any other questions about the definition of the derivative, let me know.